Welcome everyone to another seminar of Physics Latam. Today, I'm very happy and honored to have Professor Albrecht Klemm to talk about applications of Calabi-Yau periods in scattering amplitudes. Albrecht is a mathematical physicist known for his influential work in string theory, algebraic geometry, and mirror symmetry. He obtained his PhD in the 90s at the University of Heidelberg. He has made significant contributions to the study of Calabi-Yau manifolds, Gromov-Witten theory, and topological string theory, and also mirror symmetry, as I said before. He has held academic positions in institutes in Bonn University, at the BCTP, and Hausdorff Center of Mathematics. I'm very happy to have Albrecht with us today, since he was my professor during my master's degree and taught me a lot of string theory. Please remember to raise your hand at any point if there is any question, and now I leave you with Albrecht. Please go ahead.
Okay, thank you, Daniel. So so today I want to talk about or introduce you to some new applications of Calabi-Yau periods in scattering amplitude, and in the sense that periods are very interesting number theoretic objects. Also, it has to do fits in this lecture series on number theory and physics, where you also have heard talks from Spencer and will hear talks from Matt Kerr and from Mohamed Elmi. So the I mean, this is basically the work that this is based on. I'm not working very long in this area, but I realized that there is interest from this amplitude community into Calabi-Yau period integrals, and that's it's of course very good. So so the idea, maybe the general idea is that we studied period motifs. I mean, I will be, I mean, you can see the motif is a representation of the Galois group, but this plays, let's say, not the biggest role in the theory, but it is a piece of a cohomology group with some differential governed by some differential equation, whose solutions are and properties are very interesting for actual calculations, as I will show you. And we have studied these differential equations very intensively in mirror symmetry in the approach to the topological B model. And now we realized that it has some new applications to the evaluation of higher loop corrections to quantum field theory. And so it's real physics. So for instance, that is important for the precision tests of the standard model in future colliders, or also if they have more, I mean, if they have more luminosity, I mean, then and make precision experiments, they need also some higher loop corrections to be evaluated in order to make contact with the experiment. And then another thing that we did find Calabi-Yau periods is if you have Youngian integrable symmetries. For instance, you have them in N=4 super Young-Mills series, but there's models with this Youngian integrable symmetry, the so-called fishnet theories, and in these series also Calabi-Yau come up. And maybe currently for me the most exciting application is that it also plays a role in calculating the gravitational waveforms that we see in gravitational wave detection experiments, like in LIGO and further experiments that are planned. So to say it very quickly, in quantum field theory, as you know, you have to do a path integral, and this path integral is governed by this Lagrangian. And here I put some sources in order to define the correlation function as functional derivatives of this path integral with respect to the sources. And we know very well that first of all, if we do this Feynman graph expansion that emerges from that, that is an asymptotic series. And it makes, for instance, sense if we have a Lagrangian with a coupling constant, which is small. And then we can organize the contribution to these correlation functions in terms of powers of lambda. And as I said, this is an asymptotic series, but in many situations, we are far from the point of optimal truncation. Of course, in many other situations, we are not, but even for precision experiments at CERN or in this application to black hole physics, where the expansion parameter is essentially the small gravitational coupling, it makes sense to calculate higher loop orders in order to increase our predictions for physics. So that here is a scalar theory 5 to the 4, but you can easily imagine that you have a more relevant physical process than, for instance, Baba scattering, and that you need for the background at colliders in order to get it. And then the small quantity is alpha, which is 1/137. And you see here an expansion of this process in terms of this alpha. Well, in any case, if you sort of start working, let's say at this correction here, then you see that you get an integral of this form. And I should say you that when I talk about such integrals, I'm always ignoring any fermions, so any traces of gamma matrices will not appear here. So when I talk about Feynman integrals, I basically always mean the rest of the theory that remains and can be decoupled from the calculation when you do at the end the integral. So and this is a very, very let's say well established idea that these integrals, of course, they diverge, but the well-established idea is that you introduce a dimensional regularization parameter, and then you get this integral as an expansion in this dimensional regularization parameter, which is like a Lorentz series. And it is perfectly well known how to extract from these series the physical parameters that you need to calculate. So that is in all renormalizable series, which we are interested in, is not a problem. But the new thing that we have seen in the last couple of years is that the one loop integrals, then if you look at certain they're given by integrals which evaluate rational functions, and actually to iterated integrals of rational functions, in particular to the polylogarithms. And you can say these are also periods of 2 points in the Fano one-fold. So this is the Calabi-Yau. These are Calabi-Yau zero-dimensional Calabi-Yau. But then at 2 loop, you see elliptic functions, and they correspond to family of elliptic curves. And this indeed goes on, and we see higher dimensional Calabi-Yau spaces arriving that describe these integrals these functions that I have mentioned before. So you see, if you go back to this, you have here some physical parameters in it, and you make a Lorentz invariant combination of them, and then it's a function of these parameters. And what the people at LHC want from you, that you can evaluate this function super fast. That's basically why we are interested in these special functions. So as you will hopefully understand, is that this what I meant here by maximal cut integrals is not the full Feynman graph, but the full Feynman graph, the integral has boundaries. And in order to evaluate these things, you have to do iterated integrals over the Calabi-Yau periods. And for instance, while the Calabi-Yau periods themselves fulfill a homogeneous differential equation, these real Feynman graphs are related to solutions of an inhomogeneous differential equation. And I should also say that we wrote, so to say, also a little review article about that, and there are many people that contributed to that, but I can recommend you this longer article of us where it's a little bit of a review. But one thing which is maybe a paradigm change in this theory is that if you look at roughly at Cordara's map of algebraic varieties, then there are, so to say, the Fano varieties which have a positive first Chern class, and they are very simple. So, for instance, in one dimension you have just P1, and then in 2 dimensions they are classified, and in 3 dimensions they're classified. In 4 dimensions you can also this is on the way to be classified, but they are very simple. And then there is this line, which is the Calabi-Yau line, where C1 is equal 0. And that is, so to say, is beautiful. We don't know exactly whether it's finite, but there are many examples. And then if you go to negative first Chern class, then this area is more or less considered to be terrible in terms of in terms of complexity of the types that you, or of the geometries that you find. And this is a little bit opposite to what we think in string theory, because in string theory we think that maybe higher loops should be a string worldsheet expansion, where, okay, this is a Fano variety, this would be the string tree level, then you get string 1 loop, and then you get a higher genus Riemann surface, and you want to go to this direction, so to say, in this terrible direction. But what has been interesting paradigm change that we were also involved in, that maybe it's not like this. Maybe if you go to higher loops, you don't have to go to the area of higher genus Riemann surface, but rather you should go to higher dimensional Calabi-Yau manifolds, and that at least for certain class of graphs that I will show you is simply true. I mean, there are certain graph topologies that if you increase their genus, you will end up with functions that are governed by higher dimensional Calabi-Yau surfaces. So let me give you a little bit of an overview. So we have in the perturbative quantum field theory, we have this so-called maximal cut integrals. So that is if we bring the intermediate momentum on shell, and that's a relatively easy integral. And then we have the actual Feynman graph. So in the algebraic geometry realization that we need here the period integral of a Calabi-Yau, maybe epsilon deformed. I will say more about this. And the differential equation will be a Gauss-Manin type of differential equation of this type. And of course, if you want to do this in arithmetic geometry, you should actually define a period motive, and then you get an L-adic cohomology, and you get an action of the Galois group here, and you get for certain values of these integrals, you get very interesting numbers like L function values and so on. But for the Feynman graph or physics practitioner, this is less relevant. What's more relevant is the monodromy group, the question whether the monodromy group is irreducible, how you find monodromy bases that are integer, and similar things that we have often considered in string theory. Then if you go to the last line, then here you get, instead of a period integral, you get a chain integral, also epsilon deformed. Eventually, you get an inhomogeneous Gauss-Manin connection, and from the point of view of the motive, you would get an extension of this motive. So that is more or less a little roadmap to what are the physical demands and what are the mathematical structures that maybe will so to say solve these demands. So so you can ask yourself, how do I get actually practical from the Feynman graph this Gauss-Manin connection, and how do I get the inhomogeneous terms, and how do I get the epsilon expansion? And there are 2 ways, and I will give you a short account maybe in the lecture of both of these ways. The one way is to manipulate your Feynman graph into a form that it looks like a Calabi-Yau period, or like a period of an algebraic variety. And then there is another way that is a little bit more technical, but for the cases that occur, quite relevant. And that is to consider the integral as, I mean, not one integral, but a bunch of integrals. These are so-called master integrals. And here is the general type of this integral. And you will immediately recognize it looks like what I had for the bobs. So it had some physical parameters in it that I combined to Lorentz invariant parameters, and I call them x. Then it had this dimension on it, which sorry, maybe this is not to be confused with the propagator, but the thing without an index is the dimension of space-time. And as we have seen, you have eventually go away from 4-dimension in order to make this a convergent integral, and then you get this epsilon expansion. And then it is basically given by an inverse of some propagators. I mean, there can also be some kinematic terms here in the denominator, but let's see, for simplicity, it looks like this. And these propagators, they are determined by the momentum that flows through these to these legs of the graph. So everything, I mean, how this momentum flow to these individual propagators will be determined by the topology of the graph. So here I say it's just qi squared minus mi squared, but the qi can be given in terms of the external momentum and is in a momentum that I have to integrate with. And then you see something that you will normally not make in a Feynman graph. You see that I raise my propagators to some arbitrary power. This is this nu I, and this nu I are some integers. So you will quickly see why I'm doing that, because there is one relation that you will see on the next slide once we go over this, what these x's are. So the x's are, first of all, you first build certain Lorentz invariant quantities, like the mass squared or the Lorentz contraction of 2 external momentum. And the x's are actually then dimensionless quantities in that. So you want to have a dimensionless parameterization. And as I said, at the end of the day, the experimenter will ask you, how do this function depend on the x? That's what he wants to know. And we can help. So that's surprising. So first of all, I had this propagator exponent that I introduced. I call them nu. This is a vector because we have many propagators. And then I also would do my dimension here and put it all in the lattice. And then these kind of integrals are called the master integrals. And there is an interesting mathematical theory about it that I mean, this here is the most important equation, but it has nothing to do yet with the mathematical theorem. So this is an integration by parts relation, which is just due to the fact that this is an x-sub term in this integral, so it evaluates to 0. And now you can see why I put nu I in this propagators, because if I want to evaluate this expression, then since the ki or kk, as I wrote here, are inside of this propagators, I maybe raise the power of the propagator. But I get in this by this equation a differential relation between master integrals with various powers of the propagators. And so these relations, these are the IPP relations or integration by parts relations, they relate master integrals with different exponents on the propagator. And now comes, so to say, the very important and general theorem. There is a finite region in this lattice that I defined over here that contains all the non-vanishing master integrals, so that this relation closes among them, and that these relations at the end determine all these master integrals. So, so there is that is a very important fact that is used, and you when you know about Calabi-Yau periods, you will immediately recognize that looks very much like Griffith's reduction relation. Griffiths also devised an exact term that relates various periods integrals, and these from these relations you can get the Picard-Fuchs differential idea or the Gauss-Manning connection. So that is very similar here, only that's even a little bit better because you can get it for arbitrary d. So in this analogy, you should think the basis of this master integral is kind of a graph cohomology, and that would correspond in the Calabi-Yau application to the cohomology in the Calabi-Yau, and the integration by parts corresponds roughly to the Griffiths reduction formula. And then if I get a complete set of IPP relations, they correspond to the complete Picard-Fuchs ideal. That is equivalent to the Gauss-Manning connection for the period integrals. So now you can even, I mean, in this process, it's a very interesting process. But what is also quite interesting is that you have to you even have to include certain cases in which the propagator weight is 0, and you can interpret this as subgraphs. And as I will explain you, these subgraphs will give the inhomogeneous piece of the differential equation. So people, I mean, you can make here a normal ordering of these graphs, and then the ones that are in lower in this theta values, there are the subgraphs. And as I said, sorry, there is some, oops, I do something strange. Yeah. So basically, now if you use all these IPP relations on your basis of master integrals, and I've put the basis of master integrals maybe with this epsilon here, then you get such a relation. But the problem in this relation is that this A depends also on the epsilon. I mean, if you work out the IPP relation, you see you get eventually something that looks like, I mean, these are vectors. These are the vectors here now of these, or tuples of these master integrals. This is the derivative. It can be, is with respect to this parameters x. And then you get some of these linear differential equation, but it contains this epsilon. And that is not very suitable for calculations. So what you have to do is you have to make a rotation on this master integrals, and you have to find a better basis of this master integrals. And the functions that are involved in this better basis are itself interesting functions, as I will comment later on. So if you rotate these master integrals like that, then you rotate the A by this vector. This is because the rotation depends on you have a rotation action on A, and then it gets differentiated. So it's this formula, and then you have to iterate it a couple of times. But what you really want to do is to write something in which the epsilon factors out like this, and that's super important. Because when you have this form of the differential equation, then you see a couple of very interesting things. So you see, so here this is basically the vector I, but I sort of collected certain entries into P's, which are periods, and that makes some sense because these blocks here eventually become the periods. I mean, this block becomes the Gauss-Manning connection of period vectors of Calabi-Yau eventually. And there could be many Calabi-Yaus in that, and these are the diagonal blocks. And then what are these entries? So these entries are generally, in the simplest case, rational functions. Eventually, there are iterated periods of Calabi-Yau integrals. But these entries, they correspond to the subgraphs. And by that, they make the inhomogeneity of the Gauss-Manin connection. So if you write the Gauss-Manin connection for this Calabi-Yau periods, you will see it looks like a normal Gauss-Manin connection, but then there are these subgraphs, and the subgraphs are essentially the inhomogeneous pieces. So that leads you to what I said here. This leads you to this inhomogeneous Gauss-Manin connection that I have here. So that let me sort of say why this is good first. So it's good because let's say you have this connection in this form here, and you know initial conditions. Let's say for epsilon equals 0, there might be a critical dimension. And then for some particular value of the physical parameters, you know a starting value. And then you can write the EZ as a path-ordered exponential involving this matrix A, that is the best form. That is the form where the epsilon factors out. And then you can solve this integral in its epsilon dependence in terms of an iterated integral of this form. And here might be a shift in epsilon so that you get actually negative terms in epsilon, but this is, so to say, the general form. And then you get iterated integrals. And it is a very, very important question. What are these function classes of iterated integrals? So for instance, if you do this for one loop and you consider this iterated integrals, then these are all rational functions with simple poles. And then you get the famous family of the multivariable polylogarithms. Remember that these sets maybe are many variables, so it's all a little bit formal, but then you get these multiple polylogarithms. But for the higher loop amplitudes, this class has to be generalized to iterated Calabi-Yau amplitude periods. And that is the main, so to say, scientific field that has now to be explored. What is this function class that you need in order to actually calculate a real process in physics? And I show you this graph, and this graph is essentially the form of the integral, the form of this Gauss-Manin connection is basically corresponds to this one that I have here. It's just more complicated because it's for a real physical process, and the real physical process is in this case is the 5 p.m. Scattering of two black holes, which can also be described on Feynman graphs. And you see here there are these diagonals that I had before, and these diagonals can contain blocks that corresponds, let's say, to a Calabi-Yau. It can be contain blocks that will correspond to a K3, and it can most often it contains blocks which are just rational function and give sort of like polylogarithms. And you see on the right-hand side, you see all the inhomogeneities. So for instance, if you look at this K3, then it has this inhomogeneities and gives, so to say, solutions to branes on the K3, if you like, or it gives solution to the branes on the Calabi-Yau. Here, these red ones, they're supposed to be red here, and this is red. So that is how this inhomogeneous Gauss-Manin connection appears. And the example that I had before is a little bit simpler. It basically applies to the banana graph here, and you see, to the ice cone graph, and you see two types times a Calabi-Yau block, and this has to do with the kinematic of this graph. And so there are two types Calabi-Yau periods appearing that I can explain later what they are precisely. So, so as I said, these AK are normally rational function, and you get the polylogarithms, but later on you get also Calabi-Yau periods. So maybe with this block, I maybe ask question whether you ask whether you have questions to this what you heard so far.
From which paper is this?
Well, this is a good question because it's from Benjamin, has done it, and it's a forthcoming paper.
Oh, okay. And these orange part are the Fanos?
No, I mean these are, so to say, you have to imagine like in this thing that you have on the right hand side, you have the Feynman, you have these master integrals which are all relevant for the physical calculation, and then what I'm showing you is this matrix here, and I'm showing this also to you to see the complexity. It's a 232 dimensional times 232 dimensional matrix that I'm describing here. And you see in certain blocks, and these were corresponding to these blocks here, you see periods of Calabi-Yaus coming up. But in order now to do what I have showed you here, to solve the system, you need iterated integrals of Calabi-Yau periods. Is that kind of clear? And these iterated periods of the the iterated integrals of the Calabi-Yau periods are, in a sense, the analogs of multiple polylogarithms.
And you said this is a scattering of black holes, right? Is there any specific black hole, like supersymmetric black holes, or which?
No, the great thing is a not supersymmetric black hole. It's a real black hole.
Oh, okay.
That's why I refer also to these new gravitational wave experiments. So this is one of the first calculations that I did that is physically useful. Yeah. Oh, yeah. I mean,
what is the depth of the
of course, it gives higher order corrections to a process, but these higher order corrections are needed because the gravitational coupling is relatively small. So if you go to higher order in this expansion, then you can get more precision.
What is generally the depth of the iterated integrals?
Sorry?
Generally, what's the depth of the iterated integrals that you get out? Is it always depth
arbitrary?
2?
I mean, depends how many epsilon powers you need, and how many epsilon powers you need. You only see if you do the full calculation, because at the end you might want to get. I mean, if you don't look at the randomization group effects, then you have various contributions, and you look maybe at the lowest epsilon orders. But since there are several contributions, you need in very many contributions you need higher epsilon order, but usually you don't need arbitrarily high epsilon order.
And in the picture you showed us, how many iterated integrals are there?
So for this banana graph, I mean, this here for the banana graph is more like a theoretical thing that you want to calculate the banana graph in the critical dimension. So here I'm just in zeros order in epsilon, but for the black hole scattering problem, you need a couple of epsilon orders, because at the end you have to focus on the epsilon to the 0 piece of it. And I think you need 3 times iterated integrals for that.
And probably something that you mentioned earlier, but is the claim now that the Kodaira map has a natural setting in amplitudes, or?
Sorry, what is exactly the
Kodaira map? So you showed a map.
Yeah, I mean, the Kodaira. This was more like an orientation picture. So
okay, so
many. I mean, it's still very much hotly debated in the community whether it's better to work on higher genus Riemann surfaces, for instance, or whether it's better to work on Calabi-Yaus. And
sure.
Often there are actually descriptions which, I mean, there are this. I mean, you want to. I mean, the thing is that that if mathematicians look to a motive, then this motive can be realized in many ways. And often you can find the motive in a Calabi-Yau, but you can find a similar motive in a higher genus special family of a genus 2 curve. So, my taste is more a question of taste. I like to stay in this realm of Calabi-Yau manifolds. And for instance, for this particular black hole scattering problem, is all that you need. I'm not saying it's always like that, but this is the nice thing, and that's why I stole the picture from Benjamin. Is the nice thing is that is a calculation of the radiative part that you get when you do black hole scattering, and it's at the end a physical quantity that you calculate. It's not something abstract. It's really what happens when you scatter two black holes.
Last question, the 5p M2SF, what do these words mean?
I mean, 5p means that you go in in the order of post-Minkowskian order, and that means basically how many gravitational couplings you consider. And this SF, this means self-force. So there are sectors, you can do various sectors, and it's also very practical to do first in certain sectors. And so for instance, if you would go now not in the self-force sector, in the two self-force X sector, but then you would get a 1000 by 1000 matrix, unfortunately. So these calculations are very different in complexity. And yeah, so that's basically like it. So let me sort of make a short summary of what I said so far. So there are, so to say, these maximal cut integrals, they are directly related to the Calabi-Yau integrals. Then these dimensional ratios are the complex moduli of the Calabi-Yau periods. The integration by parts is the Griffiths reduction. And then the integrand of the maximal cut integral is sort of the this integrand basis is the cohomology. And the complete set of differential equations in the critical dimension is this Picard-Fuchs system. And you see these blocks in here, these blocks. And if you want to do the real calculation, you need this even homogeneity. You need to do the epsilon deformation, and that's all in this formula, basically. Then you get this iterated Calabi-Yau period integrals. So that's the summary so far. But anyway, we have maybe learned that you need Calabi-Yau period integrals, and here I sort of give you an artist sort of introduction. So here this is of course the well-known integrals of the torus. Then this is a real projection of a Kummer K3, and I also allowed myself to. I mean, this is a real projection, so this is again a two-dimensional cycle, so it's right in the dimension. And here, this is a usual way to depict the Calabi-Yau, and you see the cycles as well. But this is not a compact picture, so even so the thing is compact, it's a projection that you that is only a part of the Calabi-Yau. So these cycles run very well to infinity here. So these are these Calabi-Yau, and what we now want to do is we want to say a little bit what a Calabi-Yau is and why it's so good to calculate this is. So first of all, a Calabi-Yau is a compact, a complex manifold of complex dimension n that is scalar and has a 1-1 form, and it is also a unique nowhere vanishing n0 form that you call omega. And there are a couple of conditions that are equivalent. Most famous one is the implication from 1 to 2, because that's where for which Yau got the Fields medal. And then you can also describe it in the terms of the holonomy, which is very popular in string theory. But it's very important that low-dimensional Calabi-Yau manifolds are very simple. So, for instance, the Calabi-Yau one-fold is an elliptic curve. And it even makes sense in this context to speak of a Calabi-Yau zero-fold as being 2 points on a P1. So this even makes sense in sort of say this dimensional growing to speak about that. But in this case, you see the 1-0 form is just dx over y, and the Kähler form, the 1-1 form, is this volume form of the torus. And then okay, the torus has no holonomy. That's fine, because SU1 is trivial. But in general, you don't want to have higher dimensional tori. So you say that the holonomy should be should be SUN rather than in SUN. So that is the definition. And of course, the good thing about the Calabi-Yau is that you can easily construct it from the condition that the first Chern class vanishes. And here is the exact sequence that you use in order to get zero first Chern class. So for instance, if you take a Calabi-Yau hypersurface M in Pn plus 1, then you get this exact sequence. And if you apply the Chern classes to it, then you see that it is generated by the hyperplane class of this Pn plus 1. And then you see that the first Chern class vanishes if the degree is n plus 2. So for instance, if the degree is 3 in a P2, then you get the complex, then you get this torus, and if the degree is 5 in a P4, then you get the quintic. So from this point of view, it's very easy to construct Calabi-Yaus, and there are of course many known. So quartic in P3 is a K3, and then the quintic in P4 is a Calabi-Yau fivefold that is very well studied. And you can also easily calculate by the number of complex moduli is of course important to know, because you want to relate them to the physical quantities in your period integrals. So for instance, for the quintic it would be 101, and then you can also calculate from it the Euler number. And you can sort of get the full Hodge diamond for all these Calabi-Yaus pretty easily, and that's sort of a telephone book of the Calabi-Yau manifolds, in particular in 3 dimensions. We know that this topological data, for instance, the Hodge diamond and some intersection data classified as Calabi-Yau. So this is this theorem. So you get nice lists of Calabi-Yaus where as you can identify certain Feynman graphs if you get lucky, and that's what I did. I'm basically looking at these Feynman graphs and try to find the right Calabi-Yau. And it's also very I mean, it's also complete intersection Calabi-Yau appear a lot in this context, and that I will give you an example of that. And what also, another way of constructing Calabi-Yau is simply doing branch covers, where the branching locus is related to the canonical class of your Fano variety over which you branch. And this is also a good way of finding the Calabi-Yau that corresponds to the Feynman graph. So there are a couple of constructions of a very hands-on construction of Calabi-Yau that when some physicist presents you with a geometry of his Feynman graph, you should try to identify it with. And then, of course, what is also sort of fitting for this identification is that the complex moduli are unobstructed. So it would be strange if a physical quantity cannot live only in a certain range, because these are just external momentum and masses. So it's good that these integrals are defined simply for all these parameters, and of course, what you really look at are families, complex families over a complex moduli space of this Calabi-Yau. And here, for instance, for the quintic, you get these Hodge numbers, but the application is really to find Calabi-Yau spaces whose period integrals give the Feynman integrals in terms of where the complex moduli are these dimensionless physical quantities from the Calabi-Yau. And then you have, of course, the period integrals, and the period integrals are just this pairing between the homology and the cohomology. And you have two pairings here. One is the pairing from, as I mentioned already, by the period integrals from homology to cohomology, to C, that is the value of the period integral. And then you have also a very interesting or a very important form, sigma, that gives a pairing from the cohomology over some field to K, and this usually is Z, and that is the intersection form on the Calabi-Yau. And then, of course, you can put a basis, and it's also very important to remember that if the dimension is odd, then this is odd. I mean, if you exchange these two cycles in these forms, then you get a minus sign, like I indicated it here, and then it's actually an SPN group the choice is up to SPN, and also the monodromy is a subgroup of SPN. So this sounds all a little complicated, but the Calabi-Yau, the one-fold is the torus, is where you can still draw that. And here you see the two cycles. So this is the homology, and the cohomology we have already seen. So basically it's given by this one form, and then if you take the derivative of it, then you get a meromorphic form of second kind, and this spans your cohomology. And the integrals that you get, the period integrals, are just the elliptic integrals. It's a little bit funny for me, at least, that when Kepler solves this problem, he got elliptic integrals. Now when we do the gravitational wave sort of say calculation, we get Calabi-Yau. I mean, it's not so a higher dimensional Calabi-Yau. We get K3, and we get Calabi-Yau fourfolds. But anyway, an important feature of these things, of these period integrals, is that they always fulfill a differential equation, and that differential equation, if you write it in the first order form, it's the Gauss-Manin connection, and if you write it in, let's say, as a second order differential equation of the torus, it looks, for example, like this, and that is a very classical observation that is over 140 years old. So then what are, so to say, the main constraints that govern the period geometry of Calabi-Yau? So first is this Riemann bilinear identity relation that says that this quantity is always positive. And in fact, it has also a good meaning. So K is the Kähler potential. So this is a real quantity if you put the right powers of I here. And this is the Kähler potential for the moduli for the metric on the moduli space. And then another thing which is even more important for the Calabi-Yau people is for the Feynman graph people is this transversality condition. So what is this transversality condition meaning? So this transversality condition means that if you take one derivative of omega, then you shift in the Hodge type by 1. So for instance, on this elliptic curve, if I took one derivative, I get something which is already equivalent to the 0-1 form. And the more derivatives you take, the more you shift to the shift into these cohomology groups on the right. And before you reach the, I mean, you start with an N0 form, and before you reach here the 0N form, you get always a 0, and once you reach it, you get some algebraic function, which I call Zi, and that in string theory is known as the Yukawa coupling. So that are the two main structures that you have to remember, and both of these structures can help the calculation of Feynman graphs quite a bit. So these Hodge decomposition, and I mean, this is the explanation of these quantities 3. Sorry that there are no the labels. So these are the two pairings. And of course, if you have the periods, then you can write this with this intersection form, this pairing. So for instance, this would be the quantity that gives the Kähler form, and this gives the quantity which gives this Griffiths relation. So this one is real condition, this one is the holomorphic condition. So now I go, before I make a couple of comments how you use the structure of Calabi-Yau periods, I go to my second identification of Feynman graphs with Calabi-Yau periods, which doesn't use this IBP relation, but is more hands-on and maybe simpler to understand analytically. So if you stare at the Feynman graph, then you have two graph polynomials that are basically these are the Kirchhoff polynomials of the Feynman graph, and that you can write down. This is this U and this F. And you see the F depends on the physical parameters. It depends on the momentum and the masses. And of course, you want to write it in terms of a scale-independent variable that is Lorentz invariant. But the upshot is you get actually an integral which looks a little bit like a Calabi-Yau period integral. So let me explain it in a little bit more detail here. So first of all, you have certain exponentials. And as I said, this all comes from graph combinatorics. So for instance, here, this is the multiplicity of the vertices of the edges. And then this is the loop order, this is the dimension. And in this way, you get this exponential of the U polynomial, and similar, you get the exponential of the F polynomial. And then the integration domain is actually not a closed cycle, but it's an open cycle. So it's an open domain, and this is these are called the semantic parameterization of Feynman graphs. And if you are good at it, then you will realize that this is a Calabi-Yau manifold. So for instance, for the banana graph, you see it is like this. So the banana graph has two vertices, and then it has, I call the loop order L, so it has L plus 1 propagators. And you see, if you count this quantity, omega minus d over 2, this is actually 0. So this polynomial, this U polynomial comes with the power 0, and omega is 1. So in 2 dimensions, this U polynomial comes with power 0, and the F polynomial with power 1. And then you stare at this F polynomial, and you look at it, and you say, oh, this is a Newton polytope. And a Newton polytope is a Newton polytope of a reflexive polyhedron. So that actually already defines a form for a Calabi-Yau period. So that you know by the Griffiths form of the Calabi-Yau period. So in this way, we can identify here a Calabi-Yau hypersurface in the toric variety, which actually has the which actually describes, whose period describes this graph, or at least are very close to it. I say it's very close because this is an open domain, so it's not quite the period. But there's one thing that you also realize, that you see, if you do the counting of the physical parameter, the invariant parameters are always m squared over p squared. So they are just L plus 1 different physical parameters. And so, for instance, for the sunset graph, which is a 2-loop graph, you see there are exactly 3 physical parameters. And the Calabi-Yau, which is here in this case an elliptic curve, has 3 parameters. So that's fine. But if you go to higher dimension, then the moduli space of the physical slice here gets smaller and smaller, because the number of complex parameters grows like d squared, while the number of physical parameters only grows with d. So that is a little bit of a problem. And then we found a better realization of this Calabi-Yau, which just has this d physical parameter. And this is a complete intersection, which is given here. And you can show by a couple of transformations that it's actually equivalent to the other description. only that it has that this thing has only the physical parameters. So it's not that you just have to find the Calabi-Yau, you have also to find a nice representation of the Calabi-Yau. But for the banana graph, this is all beautifully done, and we know now, I mean, that we can describe all these banana graphs, at least the maximal cut of these types of graphs. We can describe them in terms of this simple complete intersection Calabi-Yau, whose periods have a very nice GKC system. So you can make out of this, if you are an expert, immediately a differential equation which annihilates these periods, and then you can characterize these functions. And I would say the problem of characterizing these banana graphs in any loop order is solved very nicely in one of the papers that we wrote. But these are the maximal cut integrals, and then but then there is another aspect of the approach when you get a differential equation. Of course, that is just the first step. In principle, you have to find the right period, and that's what I had already in my discussion of the IPP relations. You have to find the right initial condition for this vector. And for if you have this differential equation, you must find a particular period that is the right period. And also that is actually very much helped by the techniques that we developed for the B model in topological string. So in particular, first of all, it's good to have a monodromy, integer monodromy basis of the periods. And then there is a particular period that corresponds to the maximal cut Feynman integral, and we can figure out what this is. So another thing is that this Griffiths transversality, which was equation 3, it does something very interesting. So if you want to calculate the inverse of the Wronskian, then the inverse of the Wronskian could be, in principle, I mean, the Wronskian, remember, this is our periods and derivative of the periods. So why we want, first of all, to calculate the inverse of the Wronskian? We want to calculate the inverse of the Wronskian because we have to solve an inhomogeneous differential equation. If you solve an inhomogeneous differential equation, you have learned in the first semester that you then can do this by the variation of constant principle, and for that you need the inverse Wronskian. And then if you calculate this special solution, you need actually an iterated integral over the elements of the inverse Wronskian. But one thing which is very nice and follows from Griffiths transversality is that the inverse Wronskian is a rational function. That this inverse Wronskian can be written in terms of the intersection matrix, the Wronskian itself, which is linear in the periods and its derivative, and the matrix, which is a rational function. So in other words, while the inverse Wronskian in general could have been products of periods, and by this transcendental function of higher levels, higher transcendentality, it actually only is the original period integral times a rational function. And another thing which is nice for finding this epsilon form also is that the Gauss-Manin connection can be brought in a special form, and so on. So this many things that you know from the theory of periods of Calabi-Yau integrals are actually very interesting for calculating the inhomogeneous solution that evaluate the Feynman graphs. And the other lesson that I have here in this short lecture is that different Calabi-Yaus can have the same period structure. So it's also good to find, so to say, the most convenient realization of the Calabi-Yau. And then you have these periods are restricted by the real Griffiths relations that defines positivity of volumes, that plays a certain role in the application to super Yang-Mills theory. And anyway, we can find in this way this part of the Gauss-Manin connection that I finally identified in this huge IPP relation blocks. So that then also we have this this basis. I mean that you need a good monodromy basis to find the solution, and that you can find basically by analyzing the monodromies. And then anyway, when you want to make physical predictions like the one that we did for this black hole scattering, you need, of course, the periods at any value of its, let's say, at the real value of its physical parameter. In the case of the black hole scattering, it's unfortunately only one parameter, and you have to do the analytic continuation and so to say to evaluate your quantity. And again, for this, in order to find the integral monodromy basis, it's also good to know this analytic continuation, because then you can conjugate the vector of the period so that all the monodromies become integral. So let me make a short pause again. Are there questions to the banana graphs and how they are related to Calabi-Yaus? That was a little bit more simple, less let's say you can understand this more hands-on. You don't have to get a computer to diagonalize the IPP relations. So are there questions to this form of the integral and how you identify the Calabi-Yau in these certain blocks? I don't hear any question. Then how much time do I have?
30 minutes.
30 minutes. Okay, good. So then let me ask you, maybe do you have a prejudice whether you want to hear more about the black hole scattering or of N=4 super young Mills theory? Because I'm maybe running out of time a little bit.
Yeah, people can maybe send a message quickly on the chat.
But
do you have any preference?
If people, okay. So if there's not such a clear preference, I maybe here are some. Okay, here's somebody who, well, is different. So maybe I try to say about both things a little bit. So okay, so let's say a little bit about N=4. So this is this is about these fishnet graphs, and the fishnet graphs they are fishnet graphs with various valencies of the vertices. Here is, for instance, a 3-valent valence, and here is a 4-valent valence, and you can also have a 6-valent valence. And let us first discuss the 4-valence valence. So this is the classical fishnet graphs. So basically, you take one of these tilings of the plane, and you cut out a graph. And this graph is a graph which is a graph gives rise to an amplitude in this integrable fishnet series. So here, for instance, it is a little bit different. What is the loop order? Because here this is in the position space, so each black point is actually a loop. So so that is an 6-loop graph. So now I want to associate to this a Calabi-Yau space, and I will explain shortly how I do this. So first of all, these are fishnet graphs in 2 dimensions. This theory is already quite interesting because it has this Youngian integrable structure. And now we have here the parameters of the plane. These are the x's, and I want so the whole thing lives these external points. They live all in a P1, and also these black points, the vertices. In order to evaluate the graph, I have to integrate them over the P1. And so I get the following the following geometry. I associate to every of these black points a P1 with homogeneous coordinates x and u, and then I get this differential, which is written here. And to each point which is outside of this, each edge that is outside of this curve, this is an external parameter, because in the final amplitude, it will be, the parameters will depend on the alphas, and the x's or the xi's are integrated. So, then we have propagators, and the propagators are given like this. I mean, they have some exponent which depends on the conformal weight, and in order to get the theory conformal, then at each edge, the weights of the propagators have to add up to d, which in this case that I consider mostly is actually 2 dimensions. So now. As I said, we mainly operate with d equals 2, and then you see that you can take the propagator weight so that this condition is fulfilled all equal, and it will be for the hexagonal tiling, the propagator's weights will all be 2/3. For the quartic tiling, it will be 1/4, and for the diagonal tiling, 1/3. And now the hexagon, for the hexagonal tiling and the quartic tiling, we can associate immediately a Calabi-Yau to it. So how do I do it? So basically, I now use the construction of a Calabi-Yau as a branched covering of a Fano base. Since to each vertex I associated one P1, I have to have now the right degree in order to get a Calabi-Yau for the covering space. And it's so the base is P1 to the L, because every x was a loop. And now you can see that these Calabi-Yau that I wrote here is branched at this point. And if you count this, of course, then for each x that you have, there will be for each P1 that you have, there will be four other variables appearing in this polynomial, and that means that the Calabi-Yau condition is matched. So that is very nicely. So if here d is 2, then this thing is a Calabi-Yau by the just by the formula for the hyperplane class and the Calabi-Yau condition for the degree in terms of this hyperplane of this class in the base. So you see immediately for the quadratic tiling, if I put d equal 2, then I get a Calabi-Yau, because each vertex has 3 external legs, and that makes the degree of this polynomial that where it branches. And the same thing is true for d equals 3 for the hexagonal tiling. Interesting for the triagonal tiling doesn't work, but as you will see later, this is actually dual to the hexagonal tiling, so I don't really need it. So for these 2 tilings, I can immediately associate a Calabi-Yau to it. And then it's quite interesting that the integral, now you can actually do the integral. And the integral will be that is omega over this c. And if you think what is the definition of omega, you will see it's actually this combination of propagators. And here is an example. So for instance, if you have a graph which has 6 external legs and 2 internal legs, then it's a branched covering over P1 times P1. So it's a 3-dimensional space, and it turns out to be a K3. And you can see the pK number of this K3 I can calculate, because this K3 has singularities, and they are simply when these outer edges become equal. And so you get actually an A1 singularity at each of these points, and if you resolve them, then you see it's indeed a family of Calabi-Yau, which Picard number 17, and that has the right number of complex moduli to, it has actually 3, because you can use a conformal transformation to put 3 of this external legs to 0, 1, and infinity, so that's the right number of moduli. So this is the case 3. So the claim, or the actually what we proved in our papers, is to each graph we can associate a Calabi-Yau variety. It will be actually quite singular. So here you see it's a singular case 3, but we can resolve it in this case by blowing up all these P1s here that comes from the intersection, and then you obtain a smooth model of the Calabi-Yau in which you can calculate the periods. But essentially, you can also work with the singular Calabi-Yau. By the way, this is similar for the hexagonal tiling. That gives another case 3, which has a little bit other properties, but the counting also works. So the claim is to each graph we can associate the Calabi-Yau varieties whose periods determine this integral. And then comes the more exciting claim. So each of these integrals give rise to a Calabi-Yau motive, which depends on the dimension as either even or odd intersection form. And then we can calculate this basis with this intersection form sigma, and what the actual Feynman graph is. So that's very interesting here in this theory. This theory is simpler than the other applications, in that this Feynman graph, this integral that I have over here is actually a real so this is part of the integral, sorry. But the integral that I really want to calculate is the complex conjugate times the holomorphic piece of it. And this has to be monodromy invariant, because it's an amplitude. And the amplitude, and the only, so if the monodromy is irreducible, then the only quantity that I can put here is this quantity. And this is the Kähler, e to the Kähler parameter. So the amplitude is essentially the volume of this Calabi-Yau. So that's a very interesting and nice properties. But then you can also see what is, so to say, the application now to the Youngian symmetry of the series. So first of all, you see that there is an integrable conformal fishnet theory, which in the case of the quartic coupling is like this. So it's for the quartic fishnet graphs. And so for instance, now you have here these integrable symmetries. You have the Youngian symmetry that in 2 dimension is SO3, 1, and it splits into SL2, R and SL2, R bar. And this is generated by this algebra, conformal algebra, acting on the external parameters. This is the translation invariance, that is the rotation invariance in 2 dimensions, this is the dilatation invariance, and these are the special conformal transformations. And you have to form the Youngian of that, and the Youngian of that is actually, that is the 4th claim, and this is the most amazing claim to me, is that the Youngian is equivalent to the Picard-Fuchs differential ideal that describes the variation of hot structure of this Calabi-Yau. So that is the sort of the application of the to the n=4 Feynman graphs, and maybe you can also see that this works for the hexagonal graphs, and then you get another Calabi-Yau space. So here we need actually triple coverings of P1 to the number of loops. So for instance, here we have a Picard curve of genus 2, and then if you what is interesting is the following: you have this star triangle relation, which is very easily understand from the Youngian symmetry, and you can map whenever you have this. Sorry, this is the delta y, they call it also. This is the delta, so you can change this configuration in this configuration, and then you can instead of considering the K3 with pK number 18, you can also consider a genus 2 curve which has this form. So this is again an example in this triangle graphs. You see examples where the Calabi-Yau motif of a higher dimensional Calabi-Yau actually becomes identified by this star triangle relation of the integrable system with the period geometry of a higher genus curve. So here is that would be actually a genus 3 pK curve. I omitted the 3 here, so that is here is a Calabi-Yau threefold, and then the curve is a genus 3 pK curve. So that's very interesting. So let me come now to the last point. So this is the scattering of black holes. So that is a classical scattering, and you are giving the spin of the first black holes, and you give the mass of the first black hole and the spin of the second and the mass of the second, and then you get an impact parameter. And the question that you wanted to answer is, how much is the first black hole deflected? So this is this scattering angle. And the second thing, of course, this is gravitational effect. This is nonlinear theory, how much gravitational waves are produced in this process. Now, let me first comment on the following. Of course, this is not inspiraling of black holes. So this is not what you see in LIGO, because you need for these calculations free end states. But it calculates indeed physical quantities in this process that going into the numerical analysis of black hole mergers and are very important for that. So this calculation, this analytic calculation, is of some relevance to the black hole mergers. So here people have developed a word line formalism. So basically what you have is a word line theory which is of this form coupled to the Einstein-Hilbert action. And this is expanded in PM, means post-Minkowski approximation, and can be evaluated in this word line quantum field theory, which is an expansion around a non-trivial, around a non-interacting background. So you see here is my, I mean, if the background would not be here, then the set would not be here. And if the metric you expand in a similar way, so if it would be a straight line motion, then it would only have this term. But if you have a small perturbation to the metric around the flat background, then you add this term. And now the thing is that in this formalism, when you want to calculate from the initial data, which is the impact parameter and the incoming velocity, let's say the momentum transfer, then you can do this by a calculation which is an expansion in the gravitational coupling. So that's is of course a small quantity, and therefore it makes sense to calculate this to higher orders in the gravitational coupling. And when I talk about 5 PM post-Minkowskian evaluation, then I have here a fifth power of the gravitational coupling. And you can now calculate this in the so-called Schwinger-Keldysh in informalism in terms of a Feynman graph expansion. And the good thing is that all your Calabi-Yaus will have only one parameter, which is basically an encoding of this impact parameter. So it will be one parameter Calabi-Yau, and you see in the 4th PM approximation, you get certain Feynman graphs in the 1s sector. Sorry, this is also in the 1SF sector, what I said. So the superscript to my table should be 1SF. I'm sorry for that. So in the 2SF sector, you would get thousands of graphs, but in this case, you get only in 5 PM 232 graphs. So you get these graphs, and you get sort of a couple of more graphs that are also K3. But the only Calabi-Yau threefold that you get is a complete intersection of 4 quadrics in P7. So that's a very nice and well-known Calabi-Yau. And in the 5PM2 SF sector, which I misspoken when I looked at the graph, you see further K3 and Calabi-Yaus appearing. So this is here 1SF. I'm sorry. So this is, so to say, this map of the graphs that you need in order to do this 1SF calculation. And you see that here you get the Calabi-Yau blocks. So that is, as I said, is a concrete calculation that leads to the change in the momentum, and also to the radiation that we will present in the forthcoming paper. So let me summarize. So the conclusion maybe is that Calabi-Yau periods go very early into physics, maybe in the Kepler problem, but they have developed physically and mathematically. So now they are used for collider physics, of course, and they are used for black holes. And you see, for instance, for the banana graph, I have identified the Calabi-Yau, but they have also sort of aspects which are not, so to say, now so far very much connected, but have a great potential to be connected, because on the mathematics side, you have sort of this enumerative geometry side, which essentially is in this Feynman graphs, but I don't know what is the use of that or whatever, but it's quite remarkable. And then there's also, of course, the arithmetic geometry in this Feynman graphs, which, for instance, allows to relate them at certain values of the physical parameters to L functions of Hasselbalch zeta function and so on. That's also not very well established. But what I want to stress is that this Calabi-Yau period geometry seems to be relatively much used in physics for a reason that I don't understand at a deep level, but it's I would say it's a fact. And maybe with this I should stop my talk then.